Registered yet for secEDU, please do consider it. I think it'll be tremendous fun. Today's lecture, I am a guest lecturer and I'm going to be talking to you about hardware security. The material of all these slides was most of my day putting them together. I've stolen material from a large number of different people and also myself. I think I mined about 14 or 15 different sets of hundreds of worth of slides to get these slides today. A lot of it is brand new material as well. And yeah, I'm happy that I've had the chance to come and talk to you guys about hardware security in this security course. So to even begin with, before we even start talking about what exactly hardware security is, we have to start thinking about how do we secure any kind of computer system, to which, given that this is a security class, I hope you've all got some good ideas. So what would be some things we would do to secure a normal security system, or any computer system? Passwords. What do passwords protect? Like at a general level, they're like access control, right? So access control, that's one thing. What else might we do? Yes?
Like put in like keys where you need a key to get access to the computer system.
Yes, more access control. Two types of access control. What else might we do? Yes?
We have Windows Defender.
Windows Defender, antivirus. Yep. Yes?
Maybe like network firewall policies.
Yes. So more, that one's an interesting one actually, because that falls into access control but also falls into other categories. What else might we do? Yes?
It's access control but physical security?
Yes? Physical security as well. Presumably we might, you mentioned keys, so we might use that to encrypt stuff at rest, which is a little bit access control but a little bit not, because it's sort of also just around privacy. What else might we do? Yes? Air gapping. That's a very physical measure. Yes, that's a good one too. Air gapping is going to be one of the only ones that doesn't fall into what I'm about to just say. So we've got some ideas, right? No one here said bug finding, right? Bug finding, super important when you're thinking about security, because you might have all the best ideas in the world. You might put a super strong password thing in there and then forget that if someone just puts in no password at all, it just lets them in, right? So bug finding is super, super important. Availability is another one. It doesn't matter if you've got the most secure computer in the world if someone just unplugs it and that's got all of your important data in it. Now you haven't got access to it anymore. And of course, access control, which we come to time and time again because the foundation of security often is just ensuring who has got access to whatever you want to do. And you've circumvented this a little bit because I'm going to say, how do we now do those things? But you've already said some of them. You know, we can do air gapping, we can have strong passwords, we can do some other stuff. But pretty much everything with the exception of air gapping that we just talked about, and maybe physical security as well, does rely on assumptions. And those assumptions are that, I've got ahead of myself. Here are some other things we can do, as we were just talking about security finding, right? We can use security scanners to find bugs. We can do static application security testing, which can check for common bugs. You might have heard of things like the OWASP top 10 or the CWE top 25. These are lists of common bugs, and security scanners can find them. We can do penetration testing, and we can do audits of stuff. We can do best practice development, where when we have a password, we make sure people don't put in a 3-character one or a 1-character one. We can ensure that our employees know what they're doing, so we don't hire numpties. And then, of course, if we are going to rely on third-party stuff, we should probably ensure that those suppliers have a good reputation. I shouldn't just Google totally legit passwordmanagers.com and then integrate that into my software. Yes?
Surely it's also important to make sure that reputation is actually.
Yes. Reputation manufacturing is a thing, as are reputation attacks. But let's just assume that we have a magic wand that will tell us whether or not a given supplier actually has a good, legitimate reputation as opposed to a faked one. Right. But all of those things and everything else I said earlier all assume something. And that is that when we actually have a machine that's, for instance, running our security scanning software, or that we obtain third-party code that we're going to run on our processor, or that our penetration testing equipment, which is itself based upon software and hardware, we are assuming that that stuff is going to work correctly. We are assuming that every line of code that we write and put into our machines is going to be running on hardware that respects the intent of that software. And that is not necessarily the case, which is what I'm going to talk about today. In order for software to be secure, we have to assume that the underlying hardware is itself secure, because otherwise it's a complete can of worms. How can we verify anything if we don't actually know what the underlying hardware is doing? So when we are actually trying to do software security, for instance, or in hardware security, for a start off, we assume that the hardware that we're running our software on is actually going to execute the instructions we give it, right? We make programs. They're lists of assembly instructions which we put onto our CPU. At a bare minimum, we assume that those CPUs are going to run those instructions in roughly the order that we give them, subject to optimization and stuff like that. We also assume that the hardware is not going to run instructions we haven't provided, right? When we have a computer that's just sitting there not doing anything, we kind of want it to just sit there and not doing anything, subject to its own operating systems and Windows Defender and what have you, right? But overall, we don't want it to have some mystery instructions that have come from somewhere unexpected. So in order to achieve that, in order to have the hardware that executes the provided instructions and not other instructions or mystery instructions, when we give our circuit, given that computers are made up of circuits, to computer manufacturers, we kind of want them to build the circuit we're intending for them to build, right? That seems like a reasonable thing. I come up with a circuit which can execute x86 assembly. I then send that to a fab somewhere in the world, and I say, please make this circuit in the design that I have. And that manufacturer will send me back an integrated circuit. And I want that integrated circuit to actually have the design that I designed on it. And I also don't want it to include stuff I didn't have there, which comes back to that same problem. We don't want computer hardware to execute instructions that aren't there. And we don't want integrated circuits to have physical circuits that we didn't ask for. When it comes to software, we also often believe in a certain ideal notion of the underlying computer hardware. We like to believe that software executes without timing side effects, without power channel side effects, without other kinds of radiation, such as temperature or electromagnetic signals coming off of it. But none of those are true either. All real circuits have those properties. And so we're going to talk a little bit about that today and what we can do with it. So how do we trust these things? So I'm going to start by talking about integrated circuits. And back in the day, let's say in the 1960s and 70s, when computers were still new and fun, we had sort of vertical arrangements where a company like Commodore owned everything from the silicon mines where they got their silicon all the way up to the design house where they actually came up with the circuits, and then they actually produced those circuit chips which they installed on their own circuit motherboards, which they put into their own plastic containers and then put in the shop for you to go buy a computer made by Commodore, which is neat. But it's not very efficient, which is why we don't see Commodore Computer anymore. Doesn't really exist anymore because they got out-competed. Like with all things, it's much nicer to have companies that specialize in things. And so now the dominant form of all computer and integrated circuit production tends to be done by multiple companies working in concert. And in the case of integrated circuits, this is real common. So you might have heard of a company called TSMC, which is based out of Taiwan, or Samsung, which is based out of Korea. Between them, they make most of the integrated circuits in the world. Intel also has fabs, and they mostly make Intel chips. They do make some other ones. But for the most part, these three companies, TSMC, Samsung, and Intel, make most of the world's chips, particularly the cutting-edge ones. That means that all the other companies are actually using those guys as fabs, right? And so obviously there's some concerns there. If you want to make a circuit and you want to make it on the most fantastic cutting-edge node with the smallest feature sizes and the fastest clock circuits and the minimal power consumption, you have to rely on the advancements that these companies come up with. But can you trust them? That's the question that people and other companies are struggling with, which is why the US is making more fabs now in America, among other reasons. So the companies that don't have fabs and just sell designs to go to fabs or sell chips that are made on someone else's fabs, the percentage of their proportion of the economy just continues to grow, or the global chip economy. This is the most up-to-date graph I could get that ends in 2021. I guess some things happened in 2021 that was stopping bookkeeping. But overall, I expect these trends to have continued since 2021 as well, where we're just seeing more and more demand for designs as opposed to chips. So you might have heard of some of these companies. These are all companies that make integrated circuits, except they don't really make integrated circuits. They make designs for integrated circuits, and then they fab them on a fab's products. Right? So Apple, they have the Apple M1 and all of that sort of stuff, the Apple M2. They don't make those in-house. They make the design in-house, and then they send it off, I think, to TSMC to get it manufactured. I think the M2 used like all of the latest TSMC nodes production, so no one could even compete with them because they used the entire production line's output. ARM, obviously, is very well known. They make CPU designs, and then people put them in all sort of stuff, like Apple products. So Apple didn't even make they made bits of it, but then they also glued bits of ARM stuff in. AMD is another one, right? AMD, lots of us have AMD processors now because AMD is more competitive than Intel in some specs. But AMD doesn't make their own processors either, right? They produce designs, which then go to a fab. And on and on and on it goes. So this is the actual design flow for an integrated circuit, right? It's kind of long. We start with a specification, which is true of software as well. So you can probably relate this back to software, which you might know a bit more about. We start with a system specification, which is essentially a list of requirements, and then we produce some designs, and those designs consist of code. And you would go, that's odd. I didn't think hardware was made from code, but it is. It's made from hardware description languages, which are a bit like programming languages, but also a bit not. So we tend to write our hardware in a hardware description language. Once we've got that hardware description language, we can compile that into an actual physical circuit. That's what makes them kind of neat. Instead of compiling to a binary, we actually compile to circuits. Once we've got that circuit, we use a layouting tool to actually lay out the physical ideal components in an actual real-world space. We do some verification to make sure that that physical chip will work the way that we expect. And then once we're happy with that, we're actually going to tape it out. So we'll send it off to some company, and there's tons of steps involved in that. I've boiled them all down into a single box called fabrication. But this is the thing that gives you those big round gold wafers that people hold up in photos if they work at a fab company. Once you've got that, they literally cut that up with a laser, and they slap each one of those into a little box, and we call that packaging. And once you've done packaging, of course, you are ready to do final testing. Yes?
Is the code actually connected to the hardware, or is this like pseudocode, and then from the pseudocode you make the logic gates?
Oh, this circuit has nothing to do with that code here, if that's your question. This is a real piece of circuit. It's for a D flip-flop. This is not the diagram for a D flip-flop.
So is the code connected to the hardware, or is it?
The code, so in this case, hardware description language physically describes hardware. It's in the name. It's kind of like HTML. It's like a markup language for circuits. But a little bit more powerful than a markup language because you can describe behaviors which the synthesizer has to work out how to turn into physical hardware. If you're interested in that, you should take COMP6441, which is all about hardware description languages. Okay. There's some stuff in here in order to make this work because it's a complicated process. So for a start off, not everyone makes their own chips, and not everyone makes every part of their own chips, right? We just talked about that. Apple sticks ARM cores inside their designs. So does NVIDIA. Actually, everyone here sticks ARM cores inside their designs. So you might take an ARM core as a third-party IP block and plop it in your Apple M1 chip. Once you've done that, then you're going to do some other designs. You might have other things you need. You might need a memory controller. Nobody's inventing a memory controller after the first good memory controller. We just all pay the company that made the first good one to put it in our design as well. And you might need something like a thermometer. And you might need something like a power management circuit. And you might need something like a networking core. Nobody wants to reinvent the wheel unless the licensing terms are too onerous. So we tend to just grab individual hardware libraries in the same way that you might grab software libraries. Right? Just like in Node, there's a whole ecosystem of Node modules. This exists for the hardware world as well, which are literally pre-proved existing circuits that you can just put into your integrated circuit. That's great, except just like with the trust concerns we might have about inserting random JavaScript into our website, we also should have those same concerns about putting random circuits into our integrated circuit. So we should actually consider about the trust in there. Then, how do we actually go from these hardware description languages to an actual chip? It's a very long chain of very complex software which nobody really understands and only 2 companies in the world adequately produce. And there's not a good open source option. So you're going to be talking to Synopsys or Cadence, which are the 2 companies. You're going to pay them a very large amount of money, and then they're going to take your hardware description language and give you the final circuit diagram for it, which is very nice of them. But do you trust those tools? Probably. We don't have very much choice. Once you've got that, great, you've got your actual production files. You're now going to send that off to the fabrication house, and they're going to do the rest of it for you, and then you'll get a chip back in the mail. So I hope that A, you got your design right, and that B, they didn't mess with any of these subsequent lower steps. It gets worse. So let's say that we've now got our wonderful little chip in its wonderful little package, and we want to put that in a computer. As it turns out, the printed circuit board supply chain is even more ridiculous than the integrated circuit supply chain. Right, so we've got our little chip. We're going to go, well, I'm going to make my design. I'm going to put my chip in my design. And then at some point in this long process around the world of people putting my final printed circuit board together, my chip will actually end up in my design, which I will then sell. And that will be lovely. Except, of course, just like with the other thing, so many malicious changes can happen. And all of these have occurred in real life. We have seen designs where there have been modifications at the circuit design level. We have seen bills of material where components have been changed. We've seen the ability to compromise things like trace widths and add short circuits to designs. Counterfeit components are a huge risk. We'll talk about that more later in this presentation. Likewise with component substitution. And then finally you have your start like classic software. Sort of you'd be like, this is on the boundary of software security now, which is where after your chip is made, someone modifies with the firmware that runs on it. And then, of course, people can mess with your chips or they can modify the actual final product in transit, which is something that has been done a lot. In particular with shipments of networking gear. You can look that up on Google, something like NSA networking gear interception or something like that. And they'll talk about how they intercept shipments and then put stuff in them. So even after you make a beautifully secure product, someone can still get the container off the boat and then tamper with it. Okay. So again, back to the integrated circuit thing, it was really less of a concern when everything was happening in-house, because we had these little islands around the world that were producing stuff, and it was all in-house, and it was great, and we had Commodore computers, and we could trust them, even though they couldn't do very much. Nowadays, it's much worse, because we have a huge network of companies all over the world, each of which specializes in different tasks, and they might be under very many different legal jurisdictions, they might be under different frameworks for laws, they might not necessarily be from countries that are even, happy to be participating with other countries at that given time. I think right now there are shortages of certain rare earth minerals that are coming out of Russia because people don't want to trade with Russia right now, right? So there's lots of things that can cause problems in the supply chain of electronics. A few years ago, there were some floods in Thailand, right? And you go, floods in Thailand, that's obviously a huge problem, except it like quadrupled the cost of hard drives, because the biggest factory in the world that made hard drives was in Thailand, in the area that was flooding, right? So there's stuff like that where small local changes can have disproportionate effects on the economy and on the global sort of trade of electronic components as they move around. Obviously, COVID had a huge impact on that as well, because we saw lots of interesting stuff happen due to the shortages caused by COVID. So there are lots of risks. The first risk I want to talk about is the real obvious one, right? We've got tons of different people moving our hardware stuff around the world, and the most obvious problem, or the most obvious risk, is that one of these people modifies it in some way. So just as we have software trojans, which are like a small backdoor that you hide in some software code to do something, there is an exact analog in the hardware domain called a hardware trojan, very imaginatively named. These are fundamentally malicious modifications to designs which allow the attacker to usually control, modify, disable, or monitor the content of whatever is going on inside that circuit. This could happen at a number of different places. I've got 3 scenarios here. So you could have a malicious third-party IP. So let's assume that, for instance, ARM really wanted to mess with your day. And you go, hey, ARM, I want an ARM core in my chip. And they go, here you go, here's an ARM core. Except that the ARM core they give you has a Trojan in it so that they can monitor you. Or you might get a malicious foundry that after you give your designs to, it just compromises them and adds its own random stuff into them. Or finally, at the printed circuit board level, after you make your design and it's wonderful and it's beautiful and it doesn't have any problems with it, the factory that actually solders the chip onto your motherboard or what have you, that one's malicious. And so they just throw your chip in the bin and put something on that looks like it instead. Right? So all of these are real possibilities. And this doesn't even include the fact that you might even just have someone in-house in your own company which is making the malicious changes to your design as well. Because again, big, complicated thing. Right? So if you've got 20 million different employees working on this stuff, I think Intel has 15,000 less now, but they had tens of thousands of people that actually work on their chips. What happens if one of those people is malicious? So what are some examples of hardware Trojans in the real world? Obviously, one that happened very recently was the pager explosions in Lebanon. That's a little bit outside the scope of what we normally look at, but it is a hardware Trojan. In other ones, a long time ago, you can look this one up, is called the Clipper backdoor in 1993, which was actually just an entirely backdoored chip made by the NSA for the securing of communications in America. They were like, hey everyone, we're the NSA and we made this chip and you should use it to secure your communications. And everyone was like, no, I don't think we'll do that. It obviously had a backdoor in it. There was also a case in 2007 when there was an airstrike against Syria and all of their radars mysteriously turned off moments before the airstrike. This is likely to have been a hardware Trojan which disabled the equipment moments before the actual attack. So these are all examples of hardware Trojans in the real world, but there's plenty of academic examples as well. So the real concern with hardware Trojans is sort of covered in this article from 2008 in the IEEE Spectrum, which was called the kill switch. And it basically covered that 2007 Syrian radar in some detail. Because they said, well, how often are these kinds of kill switches, which can just turn off your critical infrastructure at will, how often are those hiding in the circuits that we actually rely on? Is there a kill switch in our phones that could just suddenly turn our phones off if a packet is broadcast over the internet and permanently disable them? Particularly since our phones already have kill circuits in them, right? Every single iPhone that's been produced in the last 5 years has got the ability to be bricked. Right? They say that's for you because, you know, if someone steals your phone, you hit the haha, fuck you button, and then it bricks their phone, right? Or your phone. But who's to say that that circuit can't be activated in other ways, right? You know, at least when there were no kill switches, you would have been real suspicious if there was a circuit in there that disabled your phone. And now we're like, oh, there's a circuit in my phone that can kill it. Excellent. I will find that useful if someone steals it. So some of the things that we would look for, we can't even look for anymore. Now we have to look at all the different ways that circuit can activate, which is a lot harder than just looking to see if that circuit is present, right? So, and it's not just phones, right? It's not just phones. There are so many critical infrastructures that are powered by computers now. Power grids, cars, traffic light systems, train network systems. There was a very famous one that happened about 6 months ago. And now I have to remember my head because I didn't put it in the slides, but I think there were some trains somewhere in Europe. Let's say Switzerland. I don't think it was Switzerland. Italy. Somewhere around there. There were some trains, and the train supplier, the company that makes trains, I guess there's not very many of them, they said that since you've bought our trains, you have to service them in our workshops because they're our trains. And the government was like, well, they're my trains because I bought them from you, and I want to service them in my workshops. And every time they took one of these trains to a non-authorized workshop, it would just mysteriously stop working. The whole train would stop working. And they'd have to get special engineers out from the company that produced them, and they're like, whoa, I don't know what you've done. You shouldn't have driven it into your workshop, I guess, with your incompatible, not our licensed tracks. And so the government got really suspicious that every time they drove one of these trains into their workshops, the train stopped working. So they engaged a cybersecurity pen testing company to hack the trains and be like, something's not right with these trains, because they work, and then they say they need a service, and then we service them, and then they're just broken until the people come and do something. And the pen testers found that all of the trains had a remote kill switch that activated every single time they entered a geo-fenced area, which just happened to be the government workshops. Right? So they were literally disabling trains just because they were driven into the wrong workshops. And then that was it. They were just disabled. Yes?
I remember reading the story. It's Poland.
Poland. There we go. I knew it was somewhere around there. So you know, these are not just theoretical attacks. These kill switches exist. And it will be really, really concerning if one day our water supply stops working because someone triggered a kill switch. So that's one of the scariest things about hardware security. Okay, what are some other things? Here is a supply chain attack. I didn't have this on the list of earlier attacks because it's controversial as to whether or not this one actually happened. But in 2020, I want to say, 2019, no, earlier than that, I've forgotten. This one's from 2021 because I can see the date here, but I think this was definitely pre-2018. Either 2017 or 2018. There was a case where someone broke the news to Bloomberg, and it's not clear who, but they said, hey, there's a really big recall or something going on with micro motherboards, super micro motherboards, which appear to have been hacked by a hardware Trojan. And the claim was that a little chip this big had been surreptitiously added to a particular wire which provided the firmware, lots of steps, to the power management controller of the chip in such a way that when the motherboard turned on, the power firmware, which had been compromised, then proceeded to compromise the main firmware by doing some buffer overflow or something, and opening a network port so that remote people could access these machines. And the first response of most people was like, that's not possible. You can't compromise the main system from the power chip and blah, 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 blah. And so this person, whose name I've forgotten, but I could probably click it, they did a demonstration at the Chaos Communication Congress, which is quite a famous cybersecurity venue, where they proved that the attack was at least possible. So they altered the wires of the board in the way that the news article sort of claimed that the wires had been altered, and they said, hey, look, this attack is at least possible, so you can't say it's not possible. As to whether or not it actually happened is hard to say, because everyone involved with the story denies that it happened, except for the reporter that reported it, to the point that the reporter did a follow-up report claiming that they were correct, which was called the long hack. So the big hack and the long hack. But it's still not necessarily settled as to whether or not this hack actually happened, but at least we know that it could have happened. And for what it's worth, this particular funding call was put out by an agency called DARPA, which you might have heard of. So they fund research in America. And they basically put out a grant that was like, hey, if this attack was to happen, come up with ways to detect and prevent it. So they at least thought that it was plausible enough to put out a funding call to get solutions for it. Okay, what are some things that aren't so malicious? How are we doing for time? What are some things that aren't so malicious? So one of the things that we're actually concerned about in the hardware security space is actually just people reverse engineering our chips. Right? If I'm ARM or I'm NVIDIA, particularly if I'm NVIDIA actually, that's a good one, I'm going to be really annoyed if someone buys my latest GPU and then rips the plastic off the top of the chip and then gets out a little microscope and looks at all the circuits and then draws it out and then goes, aha, I know the circuit diagram for the NVIDIA GPU now, and then sends it off to their own fab to produce to then compete with me. I'd be irritated about that if I was NVIDIA. So a lot of the things that we want to do is try and make that job as difficult as possible, right? So for the person or persons that would be reverse engineering our chips. Unfortunately, there's actually a lot of legitimate reasons to do reverse engineering of your chips as well. And some companies, particularly this company called ChipWorks, their whole business is just taking people's chips and reverse engineering them. So they exist to bypass those protections. And you go, well, who's paying them to do that other than interested reporters who want to report about what's going on in the latest iPhone 6? Well, actually, the most key reason that you'd be interested in what's in your competitor's chips is to know whether or not your competitor is ripping you off after somehow copying your chips. So you take your competitors' chips and then you decap them and then you look at them through the microscope and you draw out the circuit diagram and you go, aha, they haven't stolen from me, except now you've got all their circuits. And so now they're going to do the same thing to you to see if you've stolen from them. And so everyone's just reverse engineering everyone's chips all the time to try and determine who's stealing from who, if anyone. So it definitely has that sort of negation, self-pointing thing with piracy. Other things that you can do with reverse engineering is it can actually enable you to do the kinds of Trojan attacks that we were just talking about, right? So if I rip up a piece of silicon and look out with a microscope, not all of the silicon is going to be in use, right? I have a fixed amount of silicon that's usually roughly square in shape, and I can fill that in with circuits, but sometimes I have gaps, right? Just because of the nature of packing algorithms. So sometimes there will be gaps. And so if I'm a malicious person, I can look for those gaps and go, aha, there's a hole there, and I know what I could put there. I could put something malicious in there because I can reach all the wires around this hole. So that would enable you to identify sites to actually put a hardware Trojan. And then at the same time, if you're someone who just wants to know if your latest NVIDIA GPU has got a backdoor in it, you can also do a whole reverse engineering cycle and then be like, do all of these chips make sense in the context of this being a GPU, even without NVIDIA's help? And sometimes you want to do that, because imagine if you've purchased a GPU from NVIDIA, but you don't trust them. So you're like, I bought a GPU from you, but I don't know if your GPU is doing things that I want it to be doing. So I'm going to rip it to pieces and get out a microscope and look for everything and make sure everything looks like it's supposed to be there, right? And so reverse engineering has all kinds of uses. And here we are, some news articles. And so one country that's getting particularly good at reverse engineering actually is China. And so news articles about that. Oh, yeah, I remember these articles coming out when the iPhone came out, actually. OK. What can we do once we have reverse engineered things? Or rather, what can we do if we are a fabrication house that has a factory that can produce integrated circuits? Now, this is one of the biggest concerns in hardware. It's not so much of a concern in software, because to copy software, you just hit copy. To copy hardware is a little bit harder. So if you've produced a widget and you're like, I think I can sell 100,000 of these widgets for this many dollars, I am happy, I will produce 100,000 of those widgets and then I will sell them for that many dollars. But if you've now told the company that actually makes your widgets that there's a market for these widgets, and they know that what their own profit margin was by selling it to you and then you sold it to someone else, they could just build more of those widgets and then sell them themselves. Right? So this is a threat called overbuilding, and it happens a lot. Not just with electronic components, at least with electronic components we have some defenses, but it also happens with things like handbags and plastic parts in particular, because it costs exactly 0.2 of a cent to use a mold once you've created it, but creating the mold is what's actually expensive. So overbuilding is a huge problem in all kinds of hardware domains. In hardware security, we're mostly concerned about overbuilding of electronics, because I made a thing, I only licensed the factory to produce 100,000 of them, they've produced 300,000 of them. What can I do about that? What can I actually change about my design to prevent people from being able to make use of stuff they have overbuilt? So here's some examples of overbuilding. My favorite one is this one that I found out literally 3 hours ago. So there was a generator company making wind turbines. And of course, that's a kind of specialized thing, I suppose. So they came up with their designs for their wind turbines, and then they went to this company called Sinovel and said, here are our designs for our wind turbines. Can you produce us some wind turbines so we can sell them? And they did. Hooray. And then they sold the wind turbines. And then later on, they got like a ping from some software that they weren't expecting, and they were like, this says it's one of our wind turbines and it's somewhere in the world that we haven't installed any wind turbines. So they went out and had a look, and it was their wind turbines, but it wasn't their company's. As it turns out, Sinovel had just built more of their wind turbines and had just started selling them on their own. And so you can see here this rather sad sentence. So the Sinovel turbine appeared to be running a stolen version of AMSC's software. Worse, the software revealed that Sinovel had complete access to ASMC's proprietary source code, blah, 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 blah. On April the 5th, AMSC had no choice but had to announce that Sinovel now its biggest customer, accounting for more than 2/3 of the company's revenue, had stopped purchasing from them. Because why would they? They now had all of the designs. So, and that company has had a bad time since then. So the US Chamber of Commerce, because America puts out more numbers than Australia does, has estimated that it costs at least $250 billion per year due to overbuilding and piracy of various kinds. Counterfeiting. This one's fun. This is like overbuilding, except when you don't have all of the parts. So counterfeiting is where you can do a forgery or an imitation of the original components. It's like overbuilding, very closely related. It's just that they're not being made from legitimate designs, and they're usually of a much lower quality. So it is literally someone has tried to forge something as something else. This can be as drastic as taking worse versions of parts, removing all of the labeling from them, and then trying to sell them as a higher product code, and that happens. So for instance, if you buy a computer processor like an AMD one or an Intel one, right? They all look the same roughly from a physical point of view. They all have pins on the bottom and are roughly the only thing that really differentiates them is the writing on the top. So what you can do is you can just take one that's cheap, that's got writing saying it's cheap, and then you just rub out the writing, and then you put on the writing that says it's expensive, and then you go and sell that and say, hey, I've got these expensive ones to give you. And the person who buys from you won't know until it's too late, and they've actually put it in their machines that it's not as good as it is. And of course, it's not just about changing the writing. That's just only one test. You can change all sorts of stuff to try and persuade the buyer that these are the legitimate parts. If you've got internal firmware checks or something like that, they can open them up and try and compromise those checks as well, so that it really does feel like you're getting some nasty things. And if you want a really good example of counterfeiting, there's a very nice blog post by a guy that buys hard drives off Amazon and flash drives off Amazon, all the ones that are ludicrously cheap and absurdly huge, and then he proves that they are not the size capacity they claim to be when you plug them into your computer, right? So you plug in a flash drive and it goes, I am 200 terabytes, and then you write like a gigabyte to it and it's like, I'm full, because they're not actually 200 terabytes and they're just lying to you and the operating system about how much capacity they have. Now, the biggest risk of counterfeits is when you don't detect them very quickly. So one of the scary parts at the moment is that airlines at the moment, literally at the moment, are having a real problem with counterfeit components in their supply chains. And this is everything from like jet engine parts to infotainment systems to whatever else goes into planes. Steering wheels, like, I don't know. Yeah, so companies have been distributing these fake parts and then phoenixing. And so that's a huge issue. It has affected everything from the US military to commercial airlines, and it is a major concern. I'm going to come back to that slide because I want to talk about the supply chain one. So here's, this is a counterfeit from 2010 that was done in a Senate hearing. And they were talking about how there was a particular memory chip that they'd identified as counterfeit in an aircraft that had been grounded in a helicopter. And they discovered that it had been counterfeit, and they said that the reason they discovered that it was counterfeit is because it failed. Now, fortunately, it failed on the ground, so they grounded the aircraft. But they said if it hadn't failed on the ground, there's a very good chance the plane would have crashed, because it was driving one of the screens that the pilot sees the information on. And they said that these chips had been provided from a supplier, and they'd ended up in over 500 aircraft, right? So this one botched batch of counterfeit chips. So they're decidedly perturbed about the fact that counterfeit stuff is actually ending up in US military aircraft. This has been going on and on and on. This article is from 2008, but actually the most recent one I think I found was from 2023. There was a couple of companies selling fake Cisco equipment. It's not real. Obviously, the companies that are producing it have actually got pretty good clones. So you can see here that this is an example on the side there. So you've got, there's just small things, the dull screws versus shiny screws, and the length of the memory card and stuff like that. But the problem is these counterfeit components, well, A, they don't have any provenance, you have no idea what's running on them, but B, they're failing at a higher rate than the real ones would be. So you spend a lot of money getting a bunch of Cisco equipment, and then it doesn't work properly, or it has backdoors. You know, who knows? And then in 2020, there was the rather sad news that an F-16 pilot who had ejected, the ejector seat failed, and this was during a crash. So the pilot crashed in the plane. And after they tried to work out why on earth the fighter jet ejector seat didn't launch, they said there was a counterfeit part in the ejection mechanism which failed when it went to shoot him out of the canopy. So these have real-world consequences. There's so many attacks. I'm going to go through a few more of them. So some of these are older and some of them are newer. This is just a random, so you can see these aren't my slides now. I've got my color at the bottom. These are slides I have taken from other people now. But these are just a number of descriptions that I'll go through for the next few minutes on various attacks that have been published either in the real world or in the academic space. So, you know, things like smart cards. We don't use these too much for random things anymore, but we all still use the smart cards that are our credit cards. So we all still have smart cards on us, just the technology in them is changing over time. Here was an attack that got demonstrated where someone was able to, in real time, steal the signals going out of a payment terminal so that they could then reuse them in another payment terminal. So that was quite interesting. This is the case of a Mr. X who finished a PhD at UT Austin and then stole a bunch of designs from Texas Instruments, went over to China and then built those same designs. So that's an example of a malicious insider who just goes in. It's very difficult to protect against stuff like that. This is a very old one. You might have seen this. This was in a movie, I think. And back in the day, telephones would signal using a so-called out-of-band tone, which was just like it was, you know, you push the, there was a tone that could not be made from a standard keypad, which would put it into basically maintenance mode. And people worked out that a whistle that you got out of a box of cereal actually emitted that exact frequency. So when you blew the whistle into the receiver, you would put the telephone network into maintenance mode, at which point you could ask it to connect calls for free. And so this was popularized in a number of hacking movies that have, you know, every now and then you'll see someone pick up a phone and blow a whistle into it, and that's what they're referencing. This was a real thing that happened. This was happened back in 2009. I remember when people were talking about this. Back in the day, we used to measure electricity with, we still measure electricity with meters attached to your unit somewhere. Back in the day, they were mechanical meters, right? They had a thing that would rotate depending on how much electricity you were using. A meter man or a meter maid would come around and read those numbers and write them in a little book, and then later on you'd get a bill in the mail. That was too much labor, so what they decided to do was switch to electronic meters, and these electronic meters would report their signals to begin with, to a car that would drive around your neighborhood, which would just have a special receiver on it listening to all of the numbers coming out of everyone's power meters. Now obviously that has a number of problems, like if you just get the receiver, even if you're not able to change the numbers, you can tell who's at home and who isn't, because you can just look if the number's changing or not. So burglars love it. But also he worked out that it actually had a writing mode as well, and so he was able to send communications back to the meters. And the particular model that was in New Zealand, which is not on this slide, the particular model that was in New Zealand, they worked out that they could actually crack it into a firmware update, at which point you could brick the electricity meters, and we're back to the whole kill switching attacks. So there we go. This guy, though, he had a slightly more cryptographically secure smart meter, so he was able to, he had to have physical access to it, but then he was able to break the encryption inside it. Apple laptop batteries, which may be slightly more near and dear to your hearts. These have a battery, they have a chip inside them that authenticates whether or not the battery is real. This is actually kind of valuable. I used to work for a battery company, and batteries, particularly lithium-ion batteries, really like to explode. So you do actually want quite well-known parts inside your computers. Now the problem is that the particular computer that was going into, or the microcontroller that was in these batteries had some flaws, and a hacker, I guess, no, not a hacker, a Acuvant lab was able to interact with their communication protocol with that microcontroller that was in the battery and could make the battery explode. So, hooray. We're all better off for knowing that. Hotel keycards. Back in 2012, Cody Brocious, which is a great name, worked out that he could clone pretty much every hotel keycard in the world for about $20 worth of equipment. Back in 2012 again, there was a voting machine scandal in India where a company that produced these machines claimed they were invulnerable to hacking, which is a very bold claim. And some researchers proved that they could actually break into them. And although they weren't breaking the circuitry themselves, what they would do is they'd just replace the whole circuit board. This is like, if you trust the plastic box, which is the only bit that you see, we will leave the plastic box there and just change what's inside it. So yeah, the attack had a number of different steps that they could do. Hacking brain-computer interfaces. This was a really interesting one. So this is still going on at the moment with companies like Neuralink. We want to put a hat on our head and control our computer through our head. Someone worked out that in addition to the person controlling the computer, you could actually read sort of side channels out of that connection. And so they did a study similar to the ones which they already do with the brain studies, where they'd go, you know, we'll put a picture of a cat on the screen and then think about the word cat and stuff like that. Except what they did is they'd put like a picture of a cat sitting on top of a credit card and stuff like that. And so what would happen is the people would see the credit card and then think about their own credit card. And so what they were able to do is they were able to side channel out things like, did the person live in the neighborhood of the, you know, the cat would be in a neighborhood. And you're like, is that a neighborhood you recognize or not? But that wasn't the question they asked them. They could do faces they recognized, so they put the cat in front of someone they knew or vaguely like them. Birth month, credit card PIN numbers, all that sort of stuff they were able to extract in this sort of interesting side channel. All right, slightly more modern one, 2022. This was messing with the Hall sensors, which are embedded in power lines to compromise the grid. Basically, you tell the power line controller that it's not, that the sensors that it's, you know, you give it some terrible data and its embedded sensors, the grid is going to respond to that terrible data by doing things like turning parts of itself off. So that was able to happen. Compromising a two-factor key in 2022. This is, I'm not sure which key this was, but it is one of them. And using a physical attack, they were able to break out some passwords from this one. Sony, I guess you guys are probably too young for PlayStation 2s, but this was a mod chip attack on PlayStation 2s. I guess mod chips they still happen periodically, but they're a lot less common now. And so they were able to basically make this little circuit board that you could buy on the internet that you would then physically solder in the way that you see here onto the motherboard of your PlayStation 2, and then you could play pirated games on it. All right, so this was a pretty big thing. I actually knew friends in my school who had done this to their own PlayStations, so it even reached New Zealand. So I would say that, they never actually solved it. You see down the bottom here, Sony gives up on making modifications and just started making the PlayStation 3 instead. So this was a problem that they were never really able to resolve with the tools that they had available to them in the PlayStation 2 world.
I have a question.
Yes?
Why do you think they couldn't really, like, what's your opinion on why you think they couldn't really resolve this issue?
So two things. One, there was already so many places. It wasn't something you could fix with a firmware update because it was a physical hardware problem. And then the second one was, given that it's a physical hardware problem, do you go to the effort of releasing PlayStation 2 Mark VI with improved anti-piracy measures, which no one will buy, or do you just go ahead and release the PlayStation 3? Yes.
It was a different era back then.
Yeah.
When hardware needed to work without constantly being given firmware updates
Yes, yes. So there was also not the ability to do the firmware update, but inside the device had no sort of real encryption that could prevent it anyway. So there wasn't, as far as I know, there wasn't a possible firmware update that could have prevented this. Okay, back in 2005, we're all over the calendar, there was an engineer called Kostas, who, I'm probably pronouncing that wrong, who abruptly committed suicide, and then not that long, 24 hours later, they found out that this particular person was associated with a large number of hacks on a large number of the Greek cell phone network at the time, including the Prime Minister of Greece, who had it hacked, and this was all due to rogue software installed on the physical switches that managed the cell phone network. And then very lastly, a Princeton professor finds no hardware security in an e-voting machine. And you can sort of read the sort of problem here. So the voting machine had a so-called ROM chip in it, which is basically a small memory chip. It takes you 7 seconds to break into the plastic container which holds the voting machine. You then have to take 10 screws out, which doesn't take very long, and none of those are properly sealed. You then take out the ROM chip, which contains the voting machine software, put in your own ROM chip, which contains your voting machine software, seal it all back up again. You could probably do it in about 35 seconds flat. All right, so this is a sort of major concern, particularly as countries like Australia are still playing with the idea of having e-voting machines, right? They're not that good of an idea. All right, I'm going to take a 2-minute break because we're at roughly the middle of the lecture while you all have a think about what some of the solutions are to the very many problems that I have given you. Go and start thinking about solutions now. Solution number 1, my COMP6441 class. That covers all the solutions. See you all next year. No, in this for the rest of this sort of introduction to hardware security, I'm going to be talking about the sort of three main things that concern us when it comes to hardware security. And by no means this is exhaustive. There's a lot of material to hardware security. There's a lot of possible things that can happen. But these are the sorts of three core questions that we concern ourselves with in hardware security. Firstly, can we protect our designs and the data that they carry? Right? And by protect here, I mean protect against being stolen. Can we prevent our designs and the data that they carry from being stolen? Can we identify if anyone has made malicious changes to our designs? And can we identify any bugs that might be exploitable? Now, you'll notice there that identify any malicious changes to our designs doesn't necessarily concern malicious changes to the data. And that's because malicious changes to data is more of a normal software security concern, right? That's classic information security, trying to worry about people have changed data or not. And sometimes that matters to us and sometimes it doesn't. If it's just straight, like people's social security numbers or something like that, we don't care if people change those. That's a software concern. But certain data we will care about in the hardware space. So we will there's bits that matter and bits that don't. But in terms of privacy, we do care if our hardware is leaking data, and we do care if someone is stealing our hardware designs. And as for hardware bugs that might be exploitable, we'll talk a little bit more about those in a moment. So step one, how do we prevent our designs from being stolen while also protecting any data that might be on our designs? And like most things around protection and classic security, it comes back to techniques of cryptography. Now, I've got a very sort of a very big list of things that cryptography can do in the hardware space, right? So there's something called TPMs, and I have another slide on those, which I probably should have done first, but that's all right. So trusted platform modules, which are basically tiny hardware computers, which are very secure, that are inside your bigger computer. They can cryptographically ensure that your operating system itself has not been compromised, or at least the bootloader for your operating system. So you might have heard of TPMs before. Have people heard of TPMs before? Because I'll stop talking. OK, cool. So talk to those 5 hands if you want to know more about TPMs. But in terms of the other things that we've talked about, if you're worried about someone overbuilding your design or reverse engineering your design, we can actually cryptographically secure the design itself using a technique called logic locking. If we're worried about hardware trojans potentially editing our signals, say in the case of the big hack where someone was modifying the firmware as it moved from memory chip into power management integrated circuit, we could cryptographically secure the actual communications that happen on that wire. And this is something that's already happening in other protocols like TCP. We already cryptographically protect most of the information that's in the TCP protocol. So why aren't we doing it for the protocols that are actually on a physical printed circuit board? And again, if you're worried about data leakage, well, we can obviously do things like cryptographically secure data at rest and at transit. That's something we do already in the software space. But in the hardware space, what does that look like in the case of your computer? We might consider being like, in my server, which is managing people's medical records, in the actual RAM of that server are the medical records encrypted. How little time do they need to be spent decrypted so that I can do whatever it is my software actually has to do on them? Could I keep them decrypted only when they're in the actual CPU? Can I load them into the cache line and then decrypt them and then do the... So there's lots of questions like that at the actual hardware level of how much cryptography can we actually sneak in here so that everything remains secure outside of the bounds of our actual chip. If you don't happen to know what cryptography is, I would wonder why you're here, but here's a very brief introduction. Cryptography is the practice and study of techniques for secure communication in the presence of adversarial behavior. I copied that from Wikipedia 2 hours ago, so you know it's true. It is about constructing and analyzing protocols that prevent third parties or the public from reading private messages. You'll notice there's nothing about math in that definition. So calling something cryptographically secure, we sometimes use that as a term, as like a synonym for we proved that it's hard to break mathematically. But that's not actually in the definition of cryptography. And so that's why things like logic locking, which may not have a, they're not AES or DES or anything like that, you'd be like, that's not cryptography. And you're like, well, kind of is. So cryptography helps with these 3 bullet points, right? It helps keep your information private. You can use it to determine if a message is authentic or a circuit. And you can also only allow authorized parties to read it or use it in the case of a circuit. It's been around for a hot second. The first case of cryptography that we know of is in 513 BC when Hystatius of Miletus, I don't know how to pronounce that second word, shaved a slave's head and tattooed a message into it. I assume the message was in plain text and the hair was the cryptography, but that was a thing that happened and there's books on it. You might have also heard of things like Caesar ciphers, crypto quotes, other substitution ciphers like Vignier tableaus. You've probably heard of Enigma. You might have heard of its peers called Tunny and Lorenz, which are similar machines. You've probably heard of one-time pads if you know anything about cryptography. They are still considered a so-called perfect cipher because they're theoretically impossible to break if you do them right. They were used a lot in the Cold War, and they overcame the limitations of basic substitution ciphers. And we still liked substitution ciphers in the Cold War because we could do them in our head. So how did one-time pads work? They were very large, random, non-repeating keys that were just like a jumble of letters. You had one, the person you were sending a message to had one, and they were the same. They were the only two copies of that in the world. What you would do is you would then, using a substitution cipher, write your message down and then use the letters from the pad to perform the encryption. You'd transmit it, the receiver would use the letters on their pad to decrypt it, and then you'd both throw away the ones that you'd used so that you stayed in sync, and it meant that you didn't reuse keys. Reusing keys defeats the whole purpose. That's why they're called one-time pads. Obviously, they have some problems. Key synchronization means that you both need to be in a room together at some point to change books, I guess. Protecting those books was pretty tricky in the Cold War because if you had one, you were obviously a spy. They weren't sort of a thing that people just carried around with them. And then transcription errors would be a huge issue because if you skipped a letter and then the receiver didn't realize you'd skipped a letter, that would be a whole nightmare because they wouldn't be able to decrypt anything until they'd worked out how many letters you'd skipped. So yeah, they weren't perfect, but they were pretty good. Here's a picture of some one-time pad hardware. So you can see there's a little radio. This was found on a spy, so I guess they didn't do a very good job. And that is a picture of what a one-time pad actually looked like. So you can see it's sort of a jumble of letters that you would use for the substitution cipher. Yes?
Has anyone implemented a modern version of that where you use electronic data and you, for instance, like...
Fundamental. Yeah, so that's kind of how fundamental... It's actually a very similar system for things like AES and DES encryption. They just construct the pad, if you will, from a shorter key, and then the substitution is using XOR gates. So if you look at how, if you take the cryptography course, you'll learn a little bit more about that, and that's by Sushmita's cryptography course. We talk about cryptography and hardware security, but only on how to break common implementations of it, rather than the theory of them. Now, once we get bored of one-time pads and doing everything by hand, we're probably going to ask a computer to do it. The main two types of computer-powered crypto algorithms are symmetric encryption, where the sender and receiver have the same key. So this is like the one-time pad thing. And this is algorithms like DES, which nobody should use anymore, AES, which is the standard, and RC5 and other ones. I just put that one there because it's a fun little algorithm. Then there is also the so-called asymmetric key algorithms, and these ones are special, and they didn't really exist for a very long time. They rely on very advanced maths, and they are an elegant construct that lets the sender and the receiver have two different keys. Modern implementations of this are the RSA algorithm and the elliptic curve cryptography algorithms. Most websites now are protected by elliptic curve cryptography. I can probably click somewhere in here and it will tell me so. That's not the button I wanted. Let's have a look. Certificate is valid. Here we are. It is protected by something. This is easier in Firefox. Somewhere in here. Oh, no. OK, it's RSA. OK, this one's protected by RSA. But a lot of websites are now protected with ECC. OK, and again, if you're interested, this is not a lecture on cryptography, but if you happen to be interested, cryptography courses exist at UNSW. So what can we do with these things? With RSA and ECC, we can do something special because we can actually use the property of the two different keys to have a manufacturer key, right? Which is special and only the manufacturers have it. And then they can give everyone else in the world like an audience key. And they say, if you use your audience key, you can prove that I signed this piece of software with my manufacturer key. Or in the case of a website, we call that a certificate, right? Google will say, here's my public key. This is the key that makes Google Google. And whenever you visit a website, I'll sign a little piece of that website. And using your version of my key, which was public, we've told everyone about it, you can mathematically prove that I must have the secret key that goes correspondingly with this public key. And we can do that for firmware too, which is really exciting. That's what trusted platform modules are all about. So we came up with some keys, and we gave one to Microsoft, and we gave one to Apple, and we gave one to Samsung, and whoever makes hardware, they all got one. And then whoever makes operating systems, they all got one. So Ubuntu gets one, Microsoft gets one, other people who want a Mac gets one. And they then can cryptographically sign the first stage of their operating systems, the so-called bootloaders. And the reason we do that is because then the bootloader can cryptographically verify the next bit that it loads, which can verify the next bit that it loads, until eventually you've loaded your whole operating system, and you're pretty confident nobody has tampered with it. At least that's the theory. But in order for that to work, we have to have this hardware root of trust, and that's what these are really fundamentally all about. It is a root of trust that exists in your computer that's got these physical keys etched into it in a way that makes them very difficult to extract and very difficult to tamper with. And it's roughly the same principle behind what protects the key for Visa that's inside my Visa credit card, right? There is a key in there which signs transactions when I use that card. When I put it in and I enter my PIN and I buy dinner, it cryptographically signs that transaction and sends it off to Visa to say, yes, this is the real card that actually made this purchase. They used the correct PIN. You're allowed to debit the actual account. And so we do now have the ability to produce circuits which can store keys which are very, very difficult to extract. Of course, TPMs have a bit of a double-edged sword, because once people realized that we had this little blob of keys in our machine that we could use to protect the operating system, they went, I wonder what else I could protect with this. And so was born DRM, where we protect Netflix streams and Spotify songs and all kinds of stuff that I don't really feel like it needs that level of protection, but so be it. That is what it is used for as well. So the TPMs can also be used to sign and check the signatures of any arbitrary piece of software. And also, even remotely, the server that's talking to your computer can ask the TPM for verification that your computer is not trying to pirate movies or something like that. So there's lots of interesting stuff that can be done with TPMs. They were controversial at the time. Again, this may be a little bit before your time, but I remember when this blimmin' thing came out. I guess this was only 2021, and everyone was like, we have to have TPMs now. And one of my laptops doesn't have a TPM, so I couldn't upgrade. Not that I was using Windows anyway, but it was the point that mattered. All right. Yeah, and so, yeah, TPMs. Okay, I talked a little bit about in-memory encryption before. Intel has announced that they want to do it. Sure. They want to encrypt everything all the time in memory to try and prevent stuff from being compromised. AMD already has some extensions that do this. Does it work? Sometimes. So almost every type of protection in the computers nowadays has had some kind of published attack on it. Whether or not these attacks are practical remain an exercise for the reader. Certainly most of them require physical access to the machine, which does prevent a lot of attacks, because I can't just walk up to every laptop in the world. Okay, I am jumping from topic to topic, so if you want me to pause at any point, just yell out. Circuit encryption. So I mentioned that we don't just want to protect software sometimes and firmware, we actually want to protect our circuits. A neat trick that we can do is we can take our circuit diagram, which works, hooray, and then we can put a bunch of redundant gates in it, which take the form of exclusive OR gates. Exclusive OR gates are used because they have symmetry. If you put a 1 there, and it'll swap things, and if you put a 0 there, it won't swap things, so it's quite nice. And we just sort of scatter those randomly throughout our circuit, and then we say whatever the input is that didn't break the circuit when we added these, we call that our key. We call it a key. And so unless we put that same correct input to all of those random exclusive OR gates we've sprinkled like confetti through our circuit is now functionally broken and worthless. So you can see how this would immediately have some benefit. Because what we can do is we can go, I don't trust you, TSMC, with your suspiciously good nodes and fast manufacturing. I am going to take my circuit and put random exclusive OR gates through it and have lots of them, and then you'll never be able to guess what the correct input to all these random gates are. At least that's the idea. Does that work? It's never as easy as just saying something like that is going to work. There's lots of attack methods on logic locking. It's in the words of no, I won't say that. It's, in the words of this paper, been a cat and mouse game for some time. So the people who do logic locking come up with some impressive new technique, and they go, haha, this will surely protect all circuits for all time now. And then like 6 months later, the teams that break logic locking go, haha, we broke that one too. And so it has been just this very back and forth for like at least 2 decades now for the people doing logic locking and anti-logic locking. And so nothing's really been achieved in a while. Okay, what if, instead of just sprinkling random exclusive OR gates in our design, what if we took a dirty great big scalpel and just cut out a piece of it and then put in something called a field programmable gate array there instead? So we're just going to take our circuit, which we value and we love very much because we did a good job making it. We'll cut a piece of it out with scissors, and we'll put something called an FPGA in there. And what an FPGA is it's essentially reprogrammable hardware. In the same way that a CPU is reprogrammable with software, and you could have a CPU that can run different software programs, FPGAs are essentially gate arrays that can run and rerun different circuit diagrams. So once you've got an FPGA in the wild, you can just load in your circuit diagram and it will reconfigure itself to be the circuit that you actually want. Now that sounds great. Probably your first question is, hang on a second, if this technology exists, why don't we just use FPGAs everywhere and never bother with making another integrated circuit again? Well, of course, FPGAs have downsides. They're massive, so because they can be any possible circuit, they're not very good at being any one of them. They're slow because you've got all these redundant gates all of the time getting in the way of everything. And they're expensive because, again, you've got an enormous amount of redundancy for the actual design you need in there. But you can't really overcome someone taking scissors out of your designs. Or can you? Because you've got these significant space and cost overheads, obviously you're not going to redact the whole circuit, and so then it just becomes the game of, okay, they cut out this little piece of the circuit, what do we think that was in there? And that's an easier problem to solve. So trying to work out what to redact is challenging. Okay, let's pivot. Previously, up to this point, we've been kind of going, well, our foundries are the untrustworthy actor. So we're using logic locking and TPMs and stuff. We'll protect ourselves from the foundries and the factories. But what if we're not trying to protect ourselves from the foundries and the factories, but we're actually trying to protect ourselves from the users, right? I don't want chip whip or whatever they were called to take my new iPhone A5 chip and take the plastic off and then tell everyone I've got 3 GPUs in there. I don't want to do that, so what I'm going to do is I'm going to camouflage my circuit. Instead of having obvious circuits like this one here, which is a NAND gate, and this one here, which is a NOR gate, and this is what they'd look like if you went through a microscope at them, we can make a sort of crappy layout which kind of looks like both, right? So this looks like a NAND gate and a NOR gate, and the only difference is going to be how we do these 3 pillars. And the 3 pillars difficult to tell vertically. You'd have to look at the chip sideways, but then if you're looking at the chip sideways, you've got all the other pillars in the way. So it just becomes way harder to try and work out what that actual gate is. Right? So here's an example. Tell me what the difference is between those 2 things. Can you see what the difference is? Yeah, I just copied and pasted it. Right, so the real solution is these dummy contacts, and so it's very, very difficult to tell whether or not the circuit is one thing or the other. It's almost impossible from the top. Yeah, so we can overcome at least the magnifying glass. But okay, the problem is though, you can tell just from looking at this is bigger than that. And when we're trying to fit everything into 1 micron, we've not got a lot of space to play with to just say, well, sorry team, our gates are 5% bigger. Then that means you've got 5% less performance, and then AMD is going to sell more chips than you. So you're going to go, well, I can't camouflage everything. So we're back to the exact same problem. We can't camouflage every gate, so we only camouflage some of the gates. And then we're just back to the same problem as redaction, which is what do we actually camouflage? But unlike redaction and logic locking, at least people do camouflage circuits. So you can go out into the wild and decap things, and you'll actually see some of the circuits are camouflaged. So they go, okay, well, if people are actually using it, does that mean it's actually good? Maybe. There's definitely ways to defeat it. So this is the general step, or the general process that you would use to defeat a camouflage circuit, right? We don't buy just one, that would be silly. We buy 2. So I'm going to buy 2 copies of the latest Intel processor, and I'll rip the plastic and the concrete off the top of one of them, and look at all around with it on a microscope, get the circuit gates that I can, and put question marks on all the gates that I don't know. Then I'll just get another one, and then I'll run it. And what I will try and do is I will try and give it inputs that discriminate, that make me identify what possible gate each of these gates could be. So it's called coming up with discriminating inputs. And this is a whole topic on its own about how we actually come up with those inputs. So that's all I'll say about it. But suffice it to say that by using discriminating inputs, we can reduce the search space a lot. And then for the ones that we can't come up with discriminating inputs for, we just brute force them. All right, how long does that take? Not very long if you're good at it. So this is, again, a sort of future work space. All of the areas that I've talked about are future workspaces. OK, step 1's done. How are we doing for time? All right. What can we use, assuming that we've got some method of ensuring that our data and our designs are protected? What can we use to detect if our designs have been meddled with in some way, if our designs have got a hardware Trojan in them? What we're going to do is leverage something called side channel analysis. Now, this is leveraging the fact that hardware Trojans, which sneak into our designs and can do things, is that in order for a hardware Trojan to be a legitimate Trojan, it has to actually be able to do stuff. If it's just there, it's just a waste of silicon. It has to actually be connected to the system in some way that it lets it interact with it. Now, that is a bad thing in the case of, it's going to break something or cause something to explode. That's a problem. But it's a good thing for the purposes of detection, because that means we can try and hone in on the bit of the circuit that it can actually edit. So there's a number of different ways. There's a very obvious side channel called looking. So most things that have a physical presence in the universe have an observable impact on the universe in the point of view of looking at things. So we can do things like X-rays, we can take photos, and we can, I've written there, impose constraints on handling and production. I don't know why I did that. But you can take photos of things, and then we can, once we've taken the photo, we can put them in a box and put a seal on it. That's what I mean by that. Kind of like how voting ballots are distributed. We put them in a box with a sticker, and we say, don't remove the sticker. We can also take dynamic approaches. We can do runtime tests. What is a runtime test? It's we turn the circuit on, and then we measure various things about that circuit, trying to determine whether or not we can trust it or not. So here's the kind of detection principle, which hopefully is simplified by this beautiful piece of artwork that I drew myself. So we've got this idea that we've got, let's say, 2 copies of this circuit, one of which has been compromised and one of which hasn't been compromised. And we get that circuit to do stuff. And while it's doing stuff, we measure a bunch of stuff that's incidental to that. So we might measure how much power the circuit consumed. We might measure the speed at which the circuit executed. We might measure the temperature at which the circuit got to. We might measure something called HPCs, or hardware performance counters. If you've got a CPU, it has a bunch of random telemetry built into it, which we can leverage, that's the HPCs, to try and determine if they're behaving differently for some reason. we can look at electromagnetic waves coming off the chips if we're desperate for ideas. And if your design happens to have a physical component, we can also look at side channels like vibration and noise. And those are more useful than you would think, even in purely electrical systems. And then you're going to say to me, well, that's all very well and good, but this really does assume that you've got 2 copies of the circuit, one of which is trustworthy. How could you possibly assume, given everything you've told us, that you can even get one trustworthy copy of your circuit, and how would you know which was the trustworthy one? To which I would say, very good point, let's simulate the trustworthy one and just take the recordings off the real one, and we'll try and work out if the real one behaves what we expect it to from the simulation data. And then you're going to go, well, you can't trust simulations, at which point I'll say, if you can't trust a simulation, that's a software problem, not a hardware problem, so I'm not interested anymore. But you are correct, and simulations are actually extremely difficult to get right, so there are a number of problems that I'm sort of hand-waving away here. But assuming that we can get a trustworthy simulation, this becomes easier. So here's an example. This piece of work was done a couple of years ago by a group that I was involved with at New York University. So what we did is we took a Raspberry Pi and we added some hardware Trojans to the board, and we tried to work out whether or not we could detect them. We actually played a red team, blue team game where some of them had Trojans and some of them didn't, and we gave them to another student and they had to detect it using tools that we'd come up with. And they could, which was nice. Here's the piece of hardware that we developed. It was imitating an industrial controller, and the Raspberry Pi sat in the middle of it. And we had this comically large Trojan, which was just an entire Raspberry Pi Pico that we would plug into the board, and if it was there, you had a hardware Trojan, and if it wasn't, you didn't. So obviously it wasn't passing the visual test. But we got the student to remote into the boards, so they were just connected via SSH, and they had to work out if there was a Trojan or not. So here's some of the results they got. So when you have a Trojan which is capable of editing the outputs, which is very important in the case of an industrial system, anything that's actually capable of editing the outputs has to be in the actual physical output circuit. So if you create a loop where you just go output to input and then input to output and output to input, and you try and run that loop as fast as you can, like kilohertz speed, and then you measure how long it takes to, say, I don't know, do 1 million iterations of output to input to input to output to output to input. If you measure that, okay, we said 1 million, but actually it was 500. Whatever, you can do 1 million if you want, it's just going to be longer. What you can do is you can identify that there might be something there that doesn't make sense. So in the case of the straightforward detection, where we have a trustworthy model and a non-trustworthy model, you can see that, okay, this is pretty easy because the one that's not trustworthy, it takes longer by a good amount of time, actually. And then for the golden free check, where you go, could we have simulated this? Well, actually, in the data sheet for the Raspberry Pi, it actually tells you how long the input-output cycle should take. And as it turns out, that was roughly about how long we observed that it should take. But the Trojan one took way longer. So you would have been able to tell this just by reading the data sheet for the particular circuit. And then you're going to go, well, hang on a second. You did this with a really crappy Raspberry Pi Pico, right? That's a microcontroller. Yuck, that's too slow. You've told me about Trojans that can be fast and cool. So we did it again, but we did it with an FPGA. And we stuck that in as the Trojan. Now, this is purely combinational logic. There's no clock to it. So the only delay that's being added here is the physical delay of the electrons going through the wire and into the chip and then out of it again. And still, we're able to identify a relatively nice step function between the non-Trojan version and the Trojan version. So this is a reasonably good proxy for saying if you've got something in the loop that's going to output into the real world, we can at least detect those kinds of stuff. Now, what about even faster Trojans? So this was still a chip that was external to our other chip that was behaving as the Trojan. Now you could say, well, in theory, I don't need a whole external chip, right? Particularly for a lot of the real-world Trojans we've been talking about. We've been saying that Trojans could be embedded in the actual die of the chip, with maybe even just one gate. Maybe it's just a single exclusive OR gate somewhere. That will become very difficult to detect using the timing loopback. Not impossible, and some papers have talked about single gate delays, but it's definitely a lot harder because you actually need to be able to create a loop that sort of goes through that gate. And the other problem, of course, is that no two integrated circuits are made the same way. If you've got one chip that's made on a Tuesday in Taiwan and the next chip's made on Wednesday in Taiwan, they will be different chips. They will behave the same way very closely, but there will be enough process variations due to the position of the moon and the quality of the silicon and the speed of the electrons in the wires that those two chips will not behave in exactly the same way. And so when you're trying to do things like have a dirty great big Trojan that adds a big delay, easy enough to detect, if you've got a single gate worth of Trojan, that's going to be really hard because the delay that a single gate adds might be too small compared to the noise, the natural noise that's added by the process variations. But fortunately for us, Trojans usually are a level of complexity above a single gate because we want them to do things like edit memory and add networking backdoors and stuff. So those kinds of really tiny Trojans might not be practical anyway. What if we had a better way than timing? What if there's something that you can't hide from at all in the case of electric circuits, and that is power? Power consumption is something that is quite measurable, not like time, which is really fiddly. Power consumption we can measure by just connecting an ammeter in series with our circuit, and we can actually energize different parts of our chip to try and determine if the energy consumption of those parts matches what we expect. Now again, we're still going to have process variations that deal with this, but it's not as bad as you might think, particularly when you know that power consumption, particularly in gates, has very large swings depending on what that gate is actually doing. So if a gate is activated, it has a much higher power consumption than if a gate is passive. So as long as you can reliably trigger whatever your Trojan is in the circuit, you should be able to cause that energy spike, and then you might be able to see it. Now, how do we isolate the different parts of our chip? That sounds quite complicated. It is, and the only thing I will say about it is that as part of manufacturing all chips, there's a process called design for test, which essentially adds a special series of circuits in your circuit, don't worry, you actually ask for them, which let you do exactly this, that let you isolate individual networks of gates in your circuit, and they do this already for you because this is how you determine if your chip actually functions when you get it from the factory. So the design for test infrastructure is there primarily to check to make sure your chip actually works, but as a handy side effect, we can also leverage that design for test infrastructure to energize and de-energize parts of our circuit with very high accuracy. So what we're going to do in this generalized steps of power analysis is we'll choose a test pattern which can isolate parts of the hardware. Then we will use a simulation, which again can be quite accurate when it comes to power, to kind of determine how much power we would assume when we energize this particular part of the circuit. Then we'll measure the real part, we'll actually measure how much the power was consumed, and then we'll determine whether or not that was suspicious or not. And if it was suspicious, we don't have to stop there. In the timing place, we kind of have to stop because there's not so much we can do to sort of hone in on a particularly suspicious signal in the time domain. But in the power domain, we can just keep pruning. We can really get down to the individual gates to try and work out, hang on, something's funny here. And as we do that honing in, we've got sort of two objectives. Number one, we want to keep energizing the Trojan. And number two, we want to slowly prune everything that isn't the Trojan. And if we're not finding it suspicious, we can broaden our search or we can search a different area of the chip. And this is a real graph that was presented a couple of years ago at a conference. And this is exactly what they've done here. So they start with quite a broad search. And as they hone in on a suspicious signal, the total power consumption goes down because they're consuming, they're keeping less and less of the chip switched on fundamentally. But the noise or the relative energy of that Trojan keeps going up, keeps going up, keeps going up. And then there's a very dramatic drop here when they accidentally turn the Trojan off, but they realize they've done it, so they just undo that in the next step. And then they keep going up and keep going up. And at which point they've gone, this is very, very suspicious because there's no part of the circuit that should be consuming this much power at this point. But unfortunately, it's never as easy as that. Process variations do strike again, and again, if you've got small small Trojans and/or you've got large process variations, which do happen in the more modern manufacturing things, as everything gets really tiny and 2 micrometers and 1 micrometer. Process variations get very big. As we increase the variation, it reduces our chance for being able to actually detect these Trojans. So again, open problems. Good for us to have work. All right. So we can detect some modifications sometimes. What about the very last thing, which is we know that sometimes people make mistakes when they're designing stuff. When they're designing software and when they're designing hardware, sometimes mistakes are made. Those mistakes can be exploitable. Buffer overflows in the software world, which hopefully were a mistake and not deliberate. Null pointers. All of these things are exploitable, and just as they are in the software world, in the hardware world, we have an analog. And it's actually the exact same organization that tracks software bugs. So if you've heard of the software CWE taxonomy, which stands for the Common Weakness Enumeration, if you've never looked it up before, you should look it up. It's very easy to find. You just go software. I can't spell. Software. I hate this keyboard. Software CWEs. And then you go to MITRE's website, and then you can have a look at their great big taxonomy. And their taxonomy has got lots of different bugs. How do I go? Latest version. Right, it's a tree, so you can look at this, view by software development. So you can go in here and go, okay, what are all the possible types of API bugs? Use of inherently dangerous function. Let's have a look at what that means. So then it talks about what are the different things. Certain functions behave in dangerous ways regardless of how they're used, such as gets. Don't use gets, or MITRE will tell you off. And then in here it's got some other things. And it's like a tree, right? So we can sort of expand it, and then we can look at the things, and then we can go and see what's in those keys as well and stuff like that, right? So this is kind of the classification of every possible security bug in the world in software. And if you weren't aware of that, now you are, so that's great. However, we don't have to be bored in the software world because they added another button, which is hardware. So we can go do exactly the same thing, and we can look at all of the different types of bugs in the hardware space, like integration issues. Hardware child block incorrectly connected. That sounds problematic. And then it says here it's related to improper access control. We talked about that earlier. This weakness is introduced when you screw up. That's not very specific. But yes, so that's a thing that exists. So that's nice. So at least we are aware that there are possible bugs when it comes to hardware, and we can describe those bugs in a sort of classification system. However, unlike in the software space, where we take that classification system and then we go, hey, open source software companies, it'd be great if you had tools that could find when people do buffer overflows by accident, or when people do SQL injection foolishly. And we've got all kinds of scanners that can scan for those bugs in your code bases. These scanners don't yet exist for most hardware code bases. And if they do, they're expensive and they're proprietary and nobody wants to share them. So the tooling is quite rudimentary compared with the wealth of security scanners that we actually have in the hardware domain. So what do we do? Well, it's an open problem. And unfortunately, hardware bugs keep happening. So you might have heard of some of these. Spectre and Meltdown are probably the two most famous screw-ups from Intel in recent years. And these were issues in the speculative execution of their pipelines, where they have a pipeline and a processor as a long list of partially unfinished instructions, because instructions take a number of clock cycles to execute. And one of the optimizations that was invented a couple of decades ago was we could just guess if certain paths are taken in the code. So if you have an if statement in your code, one of two things can happen, right? Like if x equals 1, do this, or if x does not equal 1, do that other thing. In the hardware world, they went, this is really annoying because we get to here and we don't know, until we evaluate that, we don't know which part of the functions to start executing. So in speculative executing, we just execute both. And then eventually, when we work out which of the two paths we were supposed to take, we throw away all of the partially computed stuff that we didn't need to do. The problem with Meltdown and Spectre is people worked out that the CPUs were not adequately throwing away that stuff they shouldn't have executed in the first place. And so Spectre and Meltdown let you have side effects, timing side effects mostly, on the actual rest of your code, which you could then use to actually steal secrets from the CPU, depending on the nature of those branches. Similarly, Foreshadow was another speculative one, but I can't remember the exact details of it. Platypus was a different one. Platypus was an attack on Intel again, sorry Intel, and that one was on surreptitiously reading the power channel of the CPU. So when you go into like system monitor, I guess, on your computer, deeply buried, you can actually see the exact power consumption of your CPU at any moment in time. But as we just talked about, power consumption tells you all sorts of stuff. And they worked out there's a number of actually attacks that leverage power side channels to do things like break encryption, and that's exactly what they were able to do. Using this reader, which is just available in user space, you can ask the CPU how much power consumption it's having. They were able to do things like break encryption if the CPU was doing encryption at the time. So, whoops. Okay, so what does it look like in the case of hardware if we write something basic? I'm going to find out by asking GitHub Copilot to write hardware because it's really bad at it. So here's some hardware description language, and then I put that in, and then I asked GitHub Copilot to finish off the hardware for me. You don't worry too much about the hardware because this isn't a hardware class, but suffice to say, I'm asking it to make for me a little password-protected circuit. Okay? Now, it gave me two different options. One was a bit more confident, one was a bit less confident. And the one that was a bit more confident looked like this, where it just had a single else condition. And the one that was a little bit less confident, it gave me this other answer here, where it added another clause to my circuit. Now, if we go with the good circuit, this is fantastic. We can see that we've got our little passwordy register up here. Don't worry if you can't read circuit diagrams, but there's a little box up here which stores whether or not we're allowed to do whatever it is we want to do. And then down here is where we store our secret data that we don't want to mess with, and this other stuff in the middle controls the access to it. Great. So in the bad logic, it actually still begins roughly the same way, but then it puts this other clause in here. It just puts another else clause in there, really. So let's have a look at what happens to the circuit if we put that extra else clause in. I have lost my protection circuit. And what has happened here is that we have in our code, it doesn't look like it, but we have essentially an if true or false statement, which just defaults to just if true. So then it just defaults to, I don't need to check anymore because we're just done. And so the synthesis tool, which is like the compiler for hardware, actually detects in the same way that your compiler does if you write stupid code, that this piece of hardware is never going to be used, and so it just optimizes it away. That's great if you're trying to save money, less great if now you've lost physically the circuits that actually protect your data. And so this would be an example of a kind of rookie error, because hopefully you would catch that in some kind of functional test that, hey, your whole circuit that deals with the protection of that thing is just not there. But at the same time, if you've got a CPU-sized CPU with a million zillion transistors in it, a mistake like this can actually be quite difficult to find. So don't make them. So we did a study. Actually, that thing was in that random test that I just did. It wasn't entirely facetious. We did a study where we checked to see how many mistakes Copilot would make if it was generating hardware that had security consequences like that one you just saw. And we actually found about 30% of the time it would make those kinds of mistakes. And this stemmed, we think, from both the training data, which is really lousy for hardware, and also model limitations, and that we all know that GitHub Copilot doesn't really know anything and just sort of writes stuff that looks vaguely plausible. And you go, okay, well, how does it work in software? We did the same thing with software, and it was even worse. Copilot produces vulnerabilities about 40% of the time for C and Python. So remember that if you're using it in your job. And if you don't believe me, I'll say the same thing again, but in a whole presentation on YouTube, which you can look up because I was at Black Hat because they got me to go and talk about it there.
That's where I know you from.
Yeah, I did a Black Hat talk. How can we find these bugs? So we know that the bugs are happening. Even if Copilot doesn't make the bugs, Humans still make the bugs. Every bug that's ever existed up to this point has usually been a human's fault. So can't blame it all on Copilot. Now, similar to software, some bugs are easy to identify, right? We can read code and we can go, you have an SQL injection there. It doesn't matter what the rest of the code is. No matter what the rest of your program does, if you write your code like this, you get an SQL injection error because you've concatenated strings or something stupid like that, right? Just like that is the case for software, we have some of those bugs in hardware as well. Some bugs are really easy to spot, particularly things to do with reset logic or poorly specified state machines. They're usually easy to spot. Others can be more complex to identify, like if you're trying to deal with the fact that strange data flow problems between different parts of your circuit, or again things like speculative execution, which is apparently so difficult that they got it wrong 3 times. It's also, I've written this is a very active research area because I was running out of time. This is a very active research area, and it also happens to be my research area. So if you come and do the hardware security course, you'll hear me talk a lot more about this because this is the space in which I do most of my work. How do we actually find bugs? Just like in software, we can do things like fuzzing. There is a thing called hardware fuzzing, and it works exactly the same way as it does in the software space, where we fuzz the hardware and we try and make it crash. What does a hardware crash look like? That looks a little bit different, but typically we're trying to make it violate an assertion, which now makes it sound like software again. So we can put assertions into our hardware, we can fuzz the hardware, and then we can see if those assertions are violated. If they are, that means something's gone wrong. And that is exactly the same steps as it is for software fuzzing. So that's great. We do have a question though, which is where do we get those assertions from? Software sometimes comes with some free assertions, like don't run over the end of an array and don't dereference a null pointer, but those don't have analogs in the hardware space, right? You can run out of memory, but you've got more catastrophic problems if you've run out of memory in the hardware space. Your computer's just going to crash. So coming up with the actual properties that we need to check against is a very tricky problem. And then similarly, we can do formal verification, which again, we can do that in the software space. It's no surprise that we can do it in the hardware space as well. It's very slow, it's very computationally difficult, but it is very reliable. If you're able to formally verify something, you have proven without a shadow of a doubt that at least your properties are correct. But how do you get your properties? It's the exact same problem. It's difficult to write them, it's difficult to know what they are, and it's difficult to know that a property as specified actually prevents the bug that you're trying to prevent, which is the same problem as in the universe of software. Can we use an AI to come up with assertions for us since it's so hard? It's not a great idea, but you can. So we did this test with some people from Texas A&M University where we used a number of OpenAI's models to try and generate hardware assertions for some properties. Sort of worked. We generated 226,000 assertions, of which about 9% were useful. That does now raise the question of how do you know which 9% are useful? And so we're back to square one. But we did prove that the models could generate the assertions. So now it's just a question of how do you work out which ones are useful or not. The best model at the time was Code DaVinci 02. Since that name doesn't mean very much, that is the model that eventually became ChatGPT 3.5 with a little bit of training. In fact, ChatGPT is in this column as well. So this one became ChatGPT 3.5, but we evaluated them both. Actually, it looks like it got worse. OK, well, it was better before it was ChatGPT 3.5. Here's a lexical method for bug finding. This is still a work in progress. It's such a work in progress that I don't have a hardware slide for it yet, even though that we are doing it for hardware too. My dirty secret is that I actually do hardware and software security research because they're so similar. So in this case, we're going through and we're using a language model to help us find an SQL injection error. But we can do exactly the same thing in the hardware space as well, where we ask it to regenerate certain files and certain lines in those files, and we compare what the language model thinks it should be versus what the human developer thought it should be. And if we get inconsistencies, we then try and determine the nature of that inconsistency. Is it innocent, or is it because there is an actual bug there? This is a really nice method using a language model for bug finding because it doesn't actually require simulation. nor does it require your files to be finished, which has got to be about the only testing method in the world that can work over non-compiling files. However, it's quite noisy at the moment, and so this is still something we're working on. We've got these nice plots here which show that we are able to identify certain bugs, but we get a lot of false positives. So we're still trying to work out if it is even possible to bring down that false positive rate. How are we doing for time? Oh, we're nearly at the end of the lecture. How good. Once you've found bugs using one of the methods or an existing commercial tool, but where's the fun in that? We could ask a language model to try and fix it. That would be fun. So what we did is we made this little playground where we have a test that finds a bug, like those tests you saw earlier. And then we ask a language model to try and come up with repairs to it. And the nice thing is because language models are non-deterministic, you can kind of use them as sort of like a random mutator to come up with alternative suggestions. And you just keep doing that until one of them passes or you run out of cloud credits. So here we are. Here's an example like the one I showed you earlier. So we've got a bug where this is nothing like the one I showed you earlier. I just lied to you. This is a bug because they've written these 2 lines of Verilog code in the wrong order. When you're right, the reason that this happens is because hardware is not software. And sometimes when you're writing hardware, it matters which order you write software. Hang on, let me start that sentence again. In software, you start at the beginning and you work your way down the file. In hardware, you sometimes start at the beginning and work your way down the file. Sometimes you just execute every single line at the same time. What the person who has done here he has assumed it is the latter case where you execute every single line at the same time, but actually it's the former case where you start at the top and work your way down. And so as a result, that has a fault where they check whether or not something should be granted access after they've already granted access. Okay, so that's the fault. So we identify that that's an existing thing using a security scanner. This is not a language model-based scanner. This is an actual scanner that detected this. And so then we prompt the language model and we ask it to fix it. We can either use an autocomplete style model like the base llama models. I don't actually know if there are base llama models that aren't tuned. Okay, like models that aren't instruction tuned, or the instruction tuned model like ChatGPT, which is where you ask it what to do. Eventually you get a whole list of suggestions. You plug each of those suggestions into the file and then you test it to see if you actually have fixed the problem. Eventually you hopefully do. So this is something that does actually work. It does have some limitations. As always, there's no golden bullets here. We are able to generate fixes in a lot of different cases. And what's quite fun is that there is an actual tool called Surfix, which is like a real hardcore statistics-based people working on this for generations sort of thing that could fix some of these bugs automatically. And then we just threw language models at it and immediately outperformed them, doing no training whatsoever. Yes?
Have you tried with the GPT-4?
We will. We're getting there. These are old slides. Yeah, we were using GPT-4 and they were like, we've made it cheaper and called it O and deleted the previous model. We were like, cool, not for long.
Oh, really?
Yeah. But yeah, so again, Code DaVinci 02 was the best in this case, and GPT 3.5 was not as good. We do have some results floating around for GPT-4. Okay, so what are some key takeaways from the language model side of things? I've pivoted into language models because I work on them a lot. They performed remarkably well, particularly since none of them were trained for any of the jobs that we got them to do. Some assertions were able to be generated, and some fixes were able to be done, but mostly this was on smaller, more straightforward tasks. As soon as you got them to go above a certain level of complexity, it all fell to bits, which is honestly the case with 99% of hardware security things. Even not AI-powered stuff like formal verification. Great for toy examples, really, really hard when you've got big operating systems or full CPUs that you want to actually verify. And of course, even if you've got something, some magic bullet, whether that be classic techniques or AI techniques, to fix something that passes tests, that only means that you're passing the tests. It does not mean that it is fixed. You still have to rely on the quality of your tests. And this is something that is so true in the software space as well. Just because something is passing tests, it does not mean it is fixed. It does not mean it is good. It just means it is as good as your tests are. So that's why we'd like to bring in things like fuzzing, because they can be much more thorough than classic testing. To conclude this epic of hardware security, this was just a taste of things which I delivered with very fast so that I would get through all of my slides. Hardware security is a lot bigger than what I talked about today. There's new threats, new attacks, new capabilities coming out all the time, and in particular, new defensive stuff as well. It's not all offensive, as well as new manufacturing techniques. Here's some things I didn't talk about today, but the list goes on and on. I didn't talk about physically unclonable functions, which can help prevent you overbuilding. I talked a little bit about side channel analysis for defense. I did not tell you about side channel attacks, other than platypus. These are another way that attackers can steal your secrets. I did not tell you about fault attacks, which is another way attackers can steal your secrets. And I did not tell you about scan attacks, which are yet another way that attackers can steal your secrets. There are so many things that attackers can do to try and break into your hardware. It's very, very hard to be a defender. We did not talk much about cyber-physical attacks, which are crossover between hardware security and operational technology security, so industrial systems security. This is where the attacker leverages the real-world properties of your equipment against it. So attacks like Stuxnet, the German steel mill, where hackers melted a whole steel mill, or the Ukrainian power grid, which happened near the beginning of the war between Ukraine and Russia, where hackers, probably Russian hackers, took out quite a large portion of the Ukrainian power grid by compromising the control systems of various components. And in many ways, these are the scariest type of attacks. We're not, okay, someone stole something out of my Heartbleed or whatever. Not Heartbleed, I didn't talk about that one. Spectre or whatever. You know, that's a problem, but it's not catastrophically bad if someone gets my banking password. Okay, I can probably ring up the bank and they can undo things. But someone who blows up my wind turbine, that's much more difficult. I can't just go down the road and get another one of those. So cyber-physical attacks are kind of terrifying, and that is something we'll talk a little bit more in the hardware security course. If you are interested in anything I've talked about today, you can email me, or you can come do my course in T1 next year. This is a hands-on offensive and defensive hardware security course. We're already building some custom hardware to actually let you do the kinds of attacks I've talked about today. Thank you very much for listening. I've had great fun. Hopefully you've enjoyed learning a little bit about hardware security.